Welcome to The Explainer. Today we're diving into one of the absolute bedrock concepts in industrial control, the direct online motor starter. You could call it the simple, powerful workhorse that gets some of our heaviest machinery up and running.
All right, so here's our game plan. First, we'll figure out what a DOL starter actually is. It's one big job. Then we'll meet the key components inside the box. After that, we're going to wire it all together. First the brains, then the brawn. We'll weigh the pros and cons, and finally, see where this thing really fits into the industrial world.
Think about it for a second. You've got this huge, powerful motor that needs a ton of electricity. You obviously can't just plug it into a regular outlet or flick a light switch, right? So how do you bridge that gap between a simple human action, like pushing a button, and this powerful industrial machine?
Well, the answer is the direct online, or DOL starter. It is by far the most straightforward method out there. Its job is incredibly simple. When you hit go, it slams the motor directly onto the full raw power of the three-phase supply. And when we say three-phase, just think of it as the heavy-duty version of the power in your house, but delivered in three perfectly synchronized ways for a much more stable and powerful performance.
Okay, to really understand how it works, we need to meet the team of components inside. And first up is the real heavy lifter of the whole circuit, the contactor.
The easiest way to think of a contactor is as a giant, remote-controlled switch. It's pretty clever, actually. It uses just a tiny bit of power, a small control voltage, to energize a little coil. That coil creates a magnetic field that slams a set of massive internal contacts shut, and that action is what connects the huge motor voltage to the motor itself. It is, without a doubt, the muscle of the operation.
Next in our lineup, we have the motor's own personal bodyguard, the thermal overload relay. Its one and only job is protection.
Look, motors are expensive, and if you run them too hard, they can literally burn out. The overload relay is constantly watching the current flowing to that motor. If it senses that the motor's drawing too much power and starting to get hot, it trips. That action breaks the control circuit, which de-energizes the contactor, and the whole system shuts down safely. Think of it as a smart, resettable fuse that's going to save you from a very, very costly repair bill.
And finally, we get to the human element, the command center, where an operator tells the machine what to do. The good old-fashioned start and stop push buttons. Now this is a really key detail, so pay close attention. The start button is what we call normally open, which means there's a gap in the circuit and electricity can't flow until you press it. The stop button, on the other hand, is normally closed. That means the circuit is complete and electricity is flowing until you press it. This is a critical safety feature. Why? Because if a wire connected to the stop button were to break, the circuit would open and the machine would stop. It's designed to fail safely.
All right, let's wire this thing up. We're going to start with the brains of the operation, the low-voltage control circuit. First, we take our control power and connect it right to the input of our normally closed stop button. Safety first always. You always want the stop button to be the very first point of interruption in the control circuit.
Okay, so from the other side of that stop button, the output, we run a wire over to the input of our normally open start button. You can already see the logic here, right? Power's flowing through the stop button, and now it's just sitting there, waiting at the start button for the command to go.
Now, coming out of the start button, we connect that wire directly to the contactor's coil, which is almost always labeled A1. So the moment you press that start button, you complete the path. Power flows to that coil, the magnet energizes, and bam! Those big high-power contacts slam shut.
But hang on a second. If that's all we did, the motor would stop the instant you took your finger off the start button. So how do we keep it running? Well, this is where the real magic happens. We add something called a latching, or holding circuit. It's just one extra wire that runs in parallel with the start button, and it uses a spare auxiliary contact on the main contactor itself.
So as soon as that main contactor pulls in, this little latching contact also closes, creating a brand new path for the electricity to flow. It basically bypasses the start button and latches the circuit on. Now the only way to break this new path is to press the stop button. To finish it off, we connect the other side of the coil, A2, to neutral to complete our circuit. And just like that, the brains are fully wired.
Okay, brains are done. Time for the brawn, the high-power circuit. We start with our main three-phase power supply, L1, L2, and L3, and run it straight into a main circuit breaker for overall protection of the whole system. Coming out of that breaker, we connect our three phases directly to the main power inputs of our contactor. The high-voltage power is now sitting right there at the gate, just waiting for our little control circuit to give the command.
And this brings it all home. We connect the output terminals of the contactor, run them through our bodyguard, the thermal overload relay, and then from there, we connect them directly to the motor. And that's the whole shebang. The control circuit tells the contactor when to close, and the raw power flows right through to the motor.
So what's the bottom line here? When would you use one of these? Well, the pros are pretty clear. It's simple as can be, it's cheap, and it's easy to troubleshoot when something goes wrong. Plus, it gives you 100% of the motor's starting torque instantly. But the cons are a big deal. That direct connection creates a massive surge of current, what we call inrush, that can be 6 to 8 times the motor's normal running current. That can cause lights to dim or even trip breakers. It also creates a huge mechanical jolt, like dropping the clutch in a car. Over time, that shock can damage gears, belts, and the machinery. That's why you almost exclusively see DOL starters used on smaller motors that can handle that abrupt, powerful start.
So what's the big takeaway? The direct online starter is really the ABC of motor control. It's a foundational circuit that perfectly illustrates the core principle of separating a low-voltage control signal from high-voltage power, all while keeping things safe and functional. It's a must-know.
And that leads us to one last thought. The DOL starter is great for the little guys, but what about the true giants of industry? How do we start those massive motors without causing blackouts or literally tearing the machinery apart? Well, that's where things get even more interesting.